In this video, we're going to compute the moment of inertia of a thin spherical shell of mass big M and radius big R by slicing it into thin rings. So this is what a single thin ring slice of the shell looks like, and we're reminded in the instructions that the moment of inertia of a thin ring is given by mr squared, where little m is the mass of the ring and little r is its radius. So the strategy here is to compute the infinitesimal contribution to moment of inertia given by this thin ring, and then we're going to add up all the contributions from the bottom of the sphere to the top by using a physical integral. Before we begin, we need a quick note on area density. Area density is the mass per unit area, or mass over area. So we can write down the area density of this spherical surface as m over 4 pi r squared, since 4 pi r squared is the surface area of a sphere. And we're actually going to need this expression at the very end of our problem, so we'll stick a pin in that. Note that we can also say the total mass of the sphere is given by sigma times the area. So our mass can be expressed as sigma times A or sigma times pi r squared. But this idea that mass is given by area density multiplied by area also applies to the infinitesimal surface area contained in our thin ring slice. So we can say that the differential mass of the slice, dm, is given by sigma multiplied by dA, where dA is that differential amount of area contained in the ring. So now our plan is to find the area contained in the slice, dA, and then use the mass of the slice, dm, to find an expression for the moment of inertia of the thin ring slice. So to find the area of the thin ring, we need to know how thick it is and how far around it is. And I've started with a reminder in the diagram that the distance from the center of the sphere to the edge of the ring is still big R, the radius of the sphere. In addition, we're indicating the location of the ring by using an angle theta measured with respect to the horizontal. So to get the thickness of the ring wall, we note that we're looking at a tiny increment of arc that we'll call ds. And this arc subtends a differential angle of d theta. So if we apply the arc length formula s equals r theta to this, we could just write the thickness as ds equals r d theta. Next, to get the distance around the ring, in other words, the circumference, we need its radius, and we'll call that little r. Notice that little r becomes smaller as we get closer to the poles of this sphere, and it's maximized at the equator of the sphere. So these are changing depending on the value of theta for the ring that we're thinking about. And a bit of right triangle trigonometry tells us that little r is just big R cosine theta. Now that we know the dimensions of the ring, it's time to cut and unroll this guy to arrive at a thin rectangular slice. And the thickness is given by ds, or big R d theta, while the length is given by the original circumference of the ring when this thing was rolled up. And so that's 2 pi times little r, or 2 pi big R cosine theta. So the area of this slice, dA, is just the product of the thickness and the length, and we find a dA of 2 pi r squared cosine theta d theta. And now we can find the mass of this ring by multiplying by the area density. Remember, area density times area gives you mass. And we arrive at a mass of dm equals 2 pi sigma r squared cosine theta d theta. So now we're finally able to write down the moment of inertia contribution of this ring. Recall that the moment of inertia of a ring is just mr squared. So the moment of inertia of our thin ring, we're going to call that di because it's infinitesimal. And di is given by the mass of the ring, that's dm, times the radius of the ring, little r squared. Subbing in our expressions for dm and little r, we arrive at this huge expression for the moment of inertia contribution of a single thin ring. Now we're going to gather those factors of r together. We have 4 factors of r. And our factors of cosine, we have 3 factors of cosine, and we'll move the d theta to the end of the expression. And we arrive at our final expression for the moment of inertia contribution of our thin ring, and that's 2 pi sigma r to the 4th cosine cubed theta d theta. Note that our expression ends in a d theta, which means that's going to be our integration variable. And this expression for di indicates the moment of inertia contribution of a thin ring located at an angle of theta relative to the horizontal. This means we're going to be adding up rings all the way from negative pi over 2 at the bottom of the sphere to positive pi over 2 at the top. So those are going to become our limits of integration in just a minute. So now we need to add up all these moment of inertia contributions, and that means we're using an integral. So we write that the total moment of inertia, I, is the sum of all the contributions. Those are the di's. So there's the integral summing up infinitely many infinitesimal contributions, as integrals do. And we put in our expression for di, moving the constants out in front of the integral as we work. So there's the final setup of the integral, 2 pi sigma r to the fourth integral from negative pi over 2 to pi over 2 of cosine cubed theta d theta. And now I'm going to put on my calculus hat and pick up my pen, and we're going to grind through this classic trigonometric integral. So the first thing I notice about this integral is that the integrand is an even function. Cosine is even, and the cube of that is even as well. Because we're integrating on an interval symmetric about the origin, we're allowed now to just cut the integration interval in half and then double the result. So that's going to be my first step because I love zeros. So there's the 0 I'm going for. We cut the integration interval in half, so we're starting from 0 going to pi over 2. And I'm doubling the result. So out in front, I have a 4 now instead of a 2. And again, this is the cosine cubed of theta d theta. This is a classic trig integral, and the standard trick here is to split off a factor of cosine squared theta, which can then be expressed as 1 minus sine squared theta. Again, that 1 minus sine squared theta, that's the same thing as cosine squared, and we're left with a single factor of cosine tacked on at the end. And the whole point of this is that we're preparing ourselves to use the chain rule backwards. So in the next step, I'm going to distribute the cosine to both of these terms, and then we should be able to guess antiderivatives from that point. Okay, so we have 2 terms where we have to guess antiderivatives. The first one of these is very easy. The antiderivative of cosine is just sine. But the second one requires us to use the chain rule backwards. I have a power of the sine function here. I have sine squared, but that's sitting right next to the derivative of the sine function. This allows us to recognize the chain rule backwards. I'm just going to get a 1/3 sine cubed theta. Now, if you're not used to informally using the chain rule backwards, you just check the answer to verify what's going on here. If I differentiate 1/3 sine cubed, I have to use the chain rule, and I end up with a 1/3 times 3 sine squared. And the chain rule says multiply by the derivative of the sine function, which is that cosine we were preparing ourselves with from the beginning. So there's our antiderivative, and we're evaluating this from 0 to pi over 2. And here's why I love zeros. When I look at that lower limit, subbing that in for theta, I get sine of 0, but that's just 0. So we don't even have to worry about the lower limit. We're just going to sub in the upper limit. And the sine of pi over 2 is just 1. So I end up with a 1 minus a third, which gives me a 2/3. And when I multiply that by the 4 out in front, I end up with 8/3 pi sigma r to the fourth. Now, this isn't the expression that I remember for the moment of inertia of a thin spherical shell. And that's because we still haven't replaced the area density sigma with its expression in terms of the mass and dimensions of our shell. So if you remember that thing we stuck a pin in at the beginning of the video, that was the expression of area density as mass divided by the total area of this spherical surface, which was 4 pi r squared. And we're multiplying that by r to the fourth at the end. So things are going to start cleaning up here. I can cancel a factor of pi. I can cancel a factor of 4, leaving me with a 2 in the numerator. I can cancel 2 factors of r, leaving me with an r squared. And this cleans up to a final answer of 2/3 big M, big R squared. And that's our familiar formula for the moment of inertia of a thin spherical shell. And I can take off my calculus hat, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.